LaHouse Resource Center is a showcase of solutions for producing high-performance homes for our hot, humid climate and natural hazards, all based on results of building science research. It demonstrates a range of proven ways to gain so many benefits to enjoy every day and to have more control over our lives. Think about it. As we shape our homes, we shape our future.
The foundation comes first in every building. With good planning, you can have a great foundation. In this video, we'd like to show you some things we did at LaHouse to help improve the performance and incorporate best practices in our foundation. Stick around and we'll show you what we did. Termites cause millions of dollars in damage every year to homes. This can be prevented, however, with a good pest control program. The first line of defense is to pre-treat the soil before pouring concrete. At LaHouse, we used additional measures to prevent termite infestation. We'll show those later in the video. Building codes call for a vapor barrier under concrete slabs in residential construction to prevent moisture migration from the ground and into the home. It is important to use an approved and proven material for this purpose. Here we are spreading the vapor barrier over the entire underslab area, including the footings. Seams are lapped a minimum of 12 inches and stitched together. On the perimeter, when necessary, the edges were doweled or pinned to keep the material in place during the concrete pour. This will prevent moisture from wicking through the concrete and into the living space of the home. In the garage slab, we used a post-tension cabling system over unstable soils that tend to expand and contract. This will prevent settling and structural problems. Once the concrete is cured, the cables will be tensioned. Termites will try to get into the house any way they can, so you see here we put stainless steel screens around the pipe and snugged them up. This floor outlet has the stainless steel screen already attached, and it'll get a warning label to remind plumbers and electricians not to damage the screen. The screens block hidden pathways and force termites to reveal themselves on the exterior. And now for the big show. The concrete trucks have arrived, and the snorkel boom truck is putting the concrete where the crew needs it to trowel a smooth and level floor. Once the concrete finishers were satisfied with the finish and the location of the hardware, we covered the uncured concrete with a curing blanket to protect the concrete from the weather while it cured. When the concrete was cured enough to work on, the pest control crew returned and installed more screens wherever there were penetrations through the slab, like at these anchor bolts. Anywhere there's a place termites can get in, like at this seam or those anchor bolts, screen needs to be fastened in place and then sealed to prevent termite and pest infiltration. The framing crew is ready to start raising the walls, but before they do that, they need to install a sill sealer where the bottom plate will bolt to the foundation to prevent air from seeping underneath the bottom of the wall. Installing the sill sealer is the first step in air sealing the entire building envelope. The house is built 3 feet above base flood elevation to reduce the risk from flooding and also to reduce insurance costs. There are 3 types of foundations at LaHouse: slab cap on CMU wall, pier and beam raised wood floors, and CMU stem wall raised wood floors. For the slab on CMU stem walls, the CMUs are filled with concrete and reinforced with rebar. Then the fill is compacted, and before the concrete is poured, a plastic vapor barrier and a waterproof coating are put in place to prevent moisture from wicking into the building. The more traditional pier and beam foundation included hurricane straps to tie the floor to the foundation. Pressure-treated lumber was used here, as were corrosion-resistant fasteners to extend the life of the building. One of the 4 high-performance building systems demonstrated in the construction of LaHouse is an enhanced 2x4 wood framing used to build the midsection of LaHouse that is detailed for benefits beyond building code minimum standards. This building system uses 2x4 wall studs spaced 16 inches apart, but is enhanced with stronger, straighter engineered wood products, with fortified features to meet the design loads of a high-wind hurricane zone. with borate-treated wood for lasting protection against both decay and the destructive Formosan subterranean termite, known to cause major structural damage in only 1 year, and specially detailed for greater energy efficiency and moisture control for our hot, humid, and rainy climate. In part 2 of this video, you'll see how the enhanced 2x4 framing in LaHouse was assembled from start to finish and why. Enhanced 2x4 framing part 2, from the ground up. A sill gasket was installed along the edge of the slab under the bottom plate with dual purposes. It seals the gap under the bottom plate to stop a major source of air leakage, and it stops moisture that wicks up concrete from wetting the wood. This is known as a capillary break. Anchor bolts that were set in wet cement every 16 inches between the studs are secured with 3-inch washers for high wind resistance. Borate-impregnated laminated strand lumber, commonly called LSL studs, made from local fast-growing trees, are used instead of imported lumber. LSLs are stronger, straighter, and greatly reduce waste that commonly occurs from warpage on site as well in the production of the 2x4 lumber. Ceiling joists are engineered wood I-beams that can span wide spaces with straight, strong support for squeak-free floors above them. Like LSLs, they efficiently use local forest products and allowed us to avoid using 2x12 lumber from old-growth trees. The roof is framed with 2x8 borate pressure-treated rafters to support the weight of the tile roof. Since the roof extends over the porches, it is supported and connected to both porch columns and attic knee walls. LaHouse uses metal hurricane hardware to connect all of the components of the framing to create what's called a continuous load path from the foundation to the roof. In addition to the anchor bolts, the walls have plate-to-stud connectors on every stud to resist uplift forces, metal straps to tie window and door headers to framing and top plates, twist straps that wrap over roof rafters and connect them to the wall framing for greater resistance from the risk of splitting wood failures, and rafter straps at the roof peak to hold the two sides of the roof framing together. Borate-treated plywood wall and roof sheathing panels offer high strength and moisture performance as well as decay and termite resistance. The fortified walls are fully sheathed with 15 30-seconds thick plywood and a specified nailing pattern to resist racking, leaning forces. All edges are nailed to framing. The fortified roof decking is 19 30-seconds thick and attached with special ring shank nails at 6-inch spacing to resist pullout from uplift. Notice the decking is also marked with a grid to make installation faster and more precise. To reach the higher energy efficiency standards of LaHouse, the 2x4 framed walls were enhanced. Wall cavities are filled with sprayed cellulose insulation made from recycled newspaper with a stabilizing adhesive and a borate fire retardant, providing R13 insulating value between the studs. Sprayed insulations that fill every nook and cranny without void or compression provide about 30% better performance than typical methods. Spray foam was used on the band joist between the first and second levels to both insulate and air seal. In addition, the walls are lined with exterior rigid foam insulation panels to increase insulation value to R19 and to provide a layer of continuous insulation without the stud gaps. The front wall has a water-managed exterior insulating finish system, a synthetic stucco that allows drainage of any water that gets in. The back wall has foil-faced iso foam board with taped seams to provide insulation, radiant barrier, weather barrier, and air barrier all in one. And last but not least, windows and doors are the biggest insulation gaps in a wall. LaHouse has 10 types of insulated doors and windows that meet ENERGY STAR label criteria for the Deep South Climate Zone 2. The front door is a fiberglass skin insulated door stained to look like a beautiful wood door, only much better. The windows and back door have clear low-E glass with a very low solar heat gain coefficient to greatly reduce summer heat gain. The front porch windows are wood frame with metal cladding for low maintenance. Hurricane protection is provided by removable impact-rated fabric screens that attach to anchors in the porch archways. The back porch windows have durable composite framing from recycled material and are protected with lightweight, translucent storm panels that are easy to install on pop-open tracks. The attic in this section of LaHouse is a specially detailed unvented attic with R30 open cell spray foam under the roof decking with a fire retardant coating. Plus, knee walls are insulated to R19 like the outside walls, and no insulation on the attic floor. Why do this? It does cost more than insulating the attic floor, but can offer several benefits. Moving the insulation boundary from the ceiling to the roof line puts the air conditioner and the ductwork within conditioned space, eliminating the typically large energy losses from leaky, poorly insulated ducts in hot attics. This reduces the cooling load, so you save money by buying smaller equipment and by saving energy every day. The room ceiling below does not need to be made airtight, saving labor. And no soffit and roof vents omit the risk of wind-driven water intrusion in storms. With those benefits are important precautions to avoid problems. There should be no fuel-burning equipment in an unvented attic, unless it is the direct vent sealed combustion type. The equipment in LaHouse unvented attic is all electric. A geothermal heat pump that super efficiently heats, cools, and preheats water. There is a supply register to slightly condition the space for humidity control. The roofing underlayment should be impermeable to water vapor to prevent moisture problems. LaHouse used an adhesive membrane underlayment under the tile roofing. A few points to keep in mind. A house is a system. How it's built affects not only the energy usage, but also air quality and moisture conditions. It is possible and practical to have it all, but the details do matter. We'd also like to pass along some lessons we learned while building LaHouse. The construction workers benefit from training in both the methods and their purposes to ensure the desired outcomes. Detailed construction documents and specifications, plus a quality control system, are especially important when methods and materials deviate a little from how it's typically done. Code requirements for unvented attics, knee wall insulation materials, and other innovations can change over time with fire code changes and new knowledge. In summary, conventional 2x4 wood framing can easily be enhanced for greater energy efficiency, comfort, durability, and storm resilience. An understanding of basic building science principles, detailed specifications, and quality controls such as performance testing can help ensure the best results. With strategic trade-offs, up to 30% greater energy efficiency can be achieved with little added cost. Beyond that, upgrades do add cost, but that investment can reap greater returns. One of the 4 high-performance building systems demonstrated in the construction of LaHouse is known as advanced framing, an optimum value engineered method of wood frame construction used in the 2-story west wing of LaHouse, and revealed in cutaways in the front porch closet and the laundry room. It uses 2x6 studs spaced 24 inches apart and has been shown to cost about the same as standard framing, but with more insulation and less waste, while just as strong as traditional framing with 2x4 studs spaced 16 inches apart. Advanced framing achieves high strength, energy efficiency, and low cost by using strategic techniques that avoid unnecessary use of non-structural lumber, align openings with studs to save lumber, and takes advantage of the strength gains of stacked framing, where wall studs, ceiling joists, and roof rafters are all aligned. So, despite using wider, more expensive studs, fewer are needed, saving labor and cutting waste. The advanced framing in LaHouse was enhanced to meet the design criteria of a high-wind hurricane zone and to provide protection from the Formosan subterranean termite, the most destructive insect on the planet that can do major structural damage in 1 year. In addition to soil treatment and steel mesh termite shields, treated lumber and sheathing were used as a third layer of defense against termites and decay. The stud color indicates it is borate pressure treated. LaHouse Advanced Framing Part 2, from the ground up. A sill gasket was placed along the edge of the slab for 2 purposes. Number 1, it seals the gap under the bottom plate to stop a major source of air leakage, and number 2, it stops moisture that wicks up through the concrete from wetting the wood. This is known as a capillary break. The bottom plate was placed over the gasket and anchor bolts that had been set in wet cement every 16 inches and are secured with 3-inch washers for high wind resistance. The master bedroom and bath have raised wood floors to demonstrate alternative raised foundation systems. Both use borate pressure-treated floor joists and plywood decking for solid, no-squeak, durable floors. Floor systems are connected to piers or concrete block stem wall foundations with high load capacity hurricane foundation straps. Southern pine 2x6 lumber studs are spaced at 24 inches because wider lumber can be spaced further apart. Why do this? To have room for thicker insulation, and fewer studs mean fewer insulation gaps, creating a more energy-efficient wall. Typical wall framing uses extra studs in corners and in interior wall intersections to have a nailing surface for hanging drywall, but that creates voids with no insulation. Advanced framing uses energy corner details that allow insulation in corners and T-joint intersections. Header framing over windows and doors are sized for the load or omitted when not needed in non-load-bearing walls. This saves lumber. Notice that the double header boards are placed to the exterior, leaving room for 2.5 inches of rigid insulation where there would normally be none. It also reduces nail popping tendencies. Open web wood trusses were used between floors instead of lumber joists to allow air ductwork to run between the floors. The treated laminated strand lumber band joist between the floors provides strong stability. The band is insulated with spray foam to prevent air leaks and energy-wasting duct losses in the space between the floors. The second-story walls studs are in line over the first-level studs. Although stacked framing normally allows single top plates because of the direct alignment, LaHouse needed double top plates for its high wind load criteria. The roof is framed with rafters spaced at 24 inches, same as the wall framing. A raised top plate framing method allows insulation to fit over the exterior walls. A hip roof design is aerodynamic, so naturally is more wind resistant than other roof styles. LaHouse uses metal hurricane hardware to connect all components of the framing to create what's called a continuous load path from the foundation to the roof. LaHouse was fortified for high wind loads suitable for coastal locations. The walls have plate-to-stud connectors on every stud to resist uplift forces, corner hold-downs to resist the forces that can push or tip a building off its foundation, metal straps that tie the second level to the first level, and window headers to framing, pre-sloped U-shaped hurricane ties connecting rafters to the top plates for extra reinforcement against uplift forces on the wide roof overhang, and rafter straps at the roof peak to hold the two sides of the roof framing together. Load-bearing interior walls are also connected for high wind forces. The master bedroom wall used tall sheeting panels that cover both the bottom and the top plates. The panels are attached with a specified double nailing pattern to resist uplift as an alternative to using metal stud-to-plate connectors. This is a vented attic with ridge and soffit vents, so foil-faced roof decking was used to provide an energy-efficient radiant barrier for a cooler attic. The thicker decking is attached with ring shank nails to resist pullout from uplift. The wind-fortified walls are fully sheathed with thicker panels to resist racking or leaning forces, and are arranged so as to span and connect the first level to the second level framing. Blocking is added behind the seams so all panel edges are nailed to framing. Two termite and decay-resistant types of sheathing are exhibited at LaHouse. On the front side is borate-treated plywood, while copper-treated OSB sheathes the backside. Cellulose insulation made from recycled newspaper with a stabilizing adhesive and borate fire retardant was sprayed to fill the wall cavities, providing R19 insulating value between the studs. Sprayed insulation that fill every nook and cranny without voids or compression provide about 30% better performance than typical methods. In the attics, R38 loose-fill fiberglass was blown into the second-story attic, a low-cost option with full coverage. Specialized attic ventilation baffles allow insulation over the top plate while maintaining attic ventilation and preventing energy-wasting wind washing. This wing of LaHouse has 6 types of windows and a door that meet Energy Star label criteria for the Deep South. They have insulating clear low-E glass with a low solar heat gain coefficient to greatly reduce summer heat gain. Those in the bedrooms and master bath are also high wind pressure and impact rated, so they don't need exterior hurricane shutters. The nursery windows have metal-clad wood frames to match those on the front porch. The master bedroom has strong, energy-saving vinyl frame windows and a metal door. The sidewall has economical vinyl frame windows protected with hurricane shutters. The Bahamas-style shutters also provide attractive energy-saving shade and privacy. The back upstairs office windows have high-performance fiberglass frames with an elegant wood interior. A few points to consider. Advanced framing complies with building codes even in high wind zones, but some modifications may be needed. It uses the same skill set as conventional framing, but there is a modest learning curve before you can expect time and cost savings in the construction. Finally, if there is a concern about drywall in wet, humid weather conditions becoming wavy in 24-inch on-center spaced framing, there are several solutions. LaHouse used half-inch paperless drywall with a moisture-resistant core. Other solutions are ensuring straight framing, humidity control systems, or thicker drywall. Some lessons learned in building LaHouse. It is helpful to create and use framing drawings to ensure lumber-saving details and proper assembly of details, such as the energy corners. Workers need advanced training in both the advanced framing details and their purposes, as well as the quality controls required. Deeper wall cavities call for specialized spray insulation installation methods. So make sure your installers are trained and experienced in insulating 6-inch wall cavities. In summary, advanced framing provides higher energy efficiency at similar cost to standard framing, once past the learning curve. Fortified advanced framing for high wind and termite resistance does add cost, but offers lifetime protection for the owner's investment and peace of mind. One of the 4 high-performance building systems demonstrated in the construction of LaHouse is a structural insulated panel system, or a SIPS building system, used to build the east section of LaHouse containing the dining room and the kitchen. SIPS panels are factory-made with polystyrene foam sandwiched between wood OSB skins, creating strong building components that provide structure and insulation in one, without the conventional framing with studs and rafters. The panels range from 4 by 8 feet to 8 by 24 feet in size with various thicknesses, and can be pre-cut in the factory with window and door openings to fit the home plan, if desired. Either way, construction is fast, needs less labor, and a lot less construction waste to the landfill. SIPS creates a very energy-efficient building shell, much like a foam cooler for cold drinks. No stud framing means truly continuous insulation without gaps, voids, or compression. And SIPS buildings tend to be exceptionally tight, minimizing energy-wasting air leaks. Since termites can eat OSB and like to create superhighway tunnels through standard foam, LaHouse used SIPS with borate-treated foam and OSB to prevent costly hidden termite damage. The SIPs in LaHouse are also fortified with hurricane connectors to meet the design criteria of a high-wind hurricane zone. In part 2 of this video, you'll see how the SIPs in LaHouse was assembled from start to finish and why. LaHouse Structural Insulated Panel Building System Part 2, from the ground up. A T-shaped adhesive sill gasket was installed along the edge of the slab under the bottom plate with several purposes. Number 1, it seals the gap under the bottom plate to stop a major source of air leakage. Number 2, it stops moisture that wicks up concrete from wetting the wood. This is known as a capillary break. And number 3, it provides a built-in flashing to protect the panel and the bottom plate. For high wind resistance, a double bottom plate system was bolted to the slab at 18-inch intervals. One was inset in the SIPS panel and glued to a wider bottom plate. This made it possible to add metal plate connectors to better secure the SIPs to the bottom plates that are anchored to the foundation. The screen mesh is a stainless steel termite barrier to prevent hidden pathways. 4-inch thick panels of full wall height were set in place, and the seams were spliced together with manufactured splines resembling narrow, thinner SIPS strips. These splines provided a means to secure and seal the seams while maintaining continuity of insulation in the seams. Although the R14 insulation value is lower than the R19 used in the stud-framed walls in LaHouse, the whole wall performance of the SIPs is better because the insulation is continuous throughout, and it is airtight. To allow for on-site flexibility in building LaHouse, the SIPs panels were ordered to fit wall and roof heights, and the openings were easily cut on site. To provide structural support for the installation of windows and door units, foam was routed out along the cutout edges, making space to insert lumber to line the openings. To complete the building enclosure, LaHouse used 8-inch thick R30 panels, two alternative ways for demonstration purposes. Long panels with 2x8 rafter insets to splice the seams were raised with a crane and attached to form the roof. This creates a pre-insulated roof and an unvented attic system. Unvented, semi-conditioned attics are an easy way to keep the air conditioner and the ductwork within the conditioned space, eliminating the typically huge energy losses from ducts in hot, vented attics. This saves energy directly every day and reduces the cooling load, so a smaller, less expensive air conditioner is needed. If the roof design makes it difficult or expensive to use SIPs for the roof, they can be used as the ceiling instead, creating an airtight, fully insulated, walkable attic floor. This method was used over the home office and is visible through a SIPs knee wall at the end of the exhibit room. When SIPs form the ceiling, it is best to avoid cutting holes for light fixtures or other purposes. That would substantially reduce the energy-saving advantage of the SIPs system at a crucial location, where air leaks and heat transfer can have major impacts on home performance. So LaHouse exhibits a simple but elegant built-out kitchen lighting solution that avoids recessed fixtures. Long, specialized SIPs fasteners were used to tie the roof or ceiling panels to the walls at close intervals for wind uplift resistance. The lumber splines at 4-foot intervals were also secured with hurricane straps. SIPs panels are manufactured with preformed channels for running electrical wiring. Spaces are routed out for outlet and switch boxes wherever needed. Plumbing is best routed in interior wall framing whenever possible. When needed at an exterior wall, such as at the LaHouse kitchen, furring strips were installed to make space for piping between the panels and the drywall. Because SIPs are made of OSB and foam, it is especially important to protect the panels from water and moisture intrusion, since they don't have the same drying capacity as a wood stud building system. So LaHouse used robust window flashing systems that protect the sills and corners with sloped drainage channels. The walls were wrapped with very tear-resistant non-perforated house wrap with a low water vapor permeability rating, and seams were taped. The roof panels are protected with adhesive membrane roofing underlayment. With SIPs, windows and doors are the only insulation gaps. LaHouse has all insulated doors and windows that meet Energy Star label criteria for the Deep South, Climate Zone 2. The side doors are fiberglass skin insulated doors with low-E insulated glass. The windows have clear low-E glass with a very low solar heat gain coefficient to greatly reduce summer heat gain. In the kitchen, the windows have durable, efficient fiberglass frames and are protected from windborne debris with economical accordion shutters. The home office windows have treated wood frames for decay and termite resistance. The front window is protected with decorative hinged board and batten hurricane impact shutters. A few points to consider. SIPs homes typically cost 1 to 3% more than standard framing for custom home designs, but production builders can optimize labor and time savings to offset the higher material cost. Since there is always a learning curve in new methods, training and experience are important to ensure the most cost-effective results. An advantage of SIPs is that it results in an energy-efficient, airtight building with much less effort and attention to detailed workmanship. Yet, as with any high-performance home, it is important to build tight but ventilate right. So LaHouse has not only right-sized efficient cooling and heating systems, but also ducted, filtered fresh air ventilation with damper flow controllers to get clean, controlled fresh air, and a supplemental energy-efficient dehumidifier to maintain comfortable, healthy, relative humidity below 50% regardless of whether or not any cooling is needed. Lessons learned in building LaHouse SIPs section include: high wind connection methods are different for SIPs. Load calculations and specifications should be clearly determined before finalizing the designs and beginning the construction. Even if the construction crew is trained, other trades, such as electricians and plumbers, may be unfamiliar with how to efficiently install their systems in SIPs. Time, labor, construction waste, and material errors can be further reduced when construction plans are provided to the SIPs manufacturer to pre-cut all the openings. In summary, SIPs create a strong and highly energy-efficient building with less reliance on detailed workmanship to achieve a tight building. Experienced SIPs builders and designers are less plentiful, but the technology is mature and has been well researched and verified. One of the 4 high-performance building systems demonstrated in the construction of LaHouse is the insulating concrete form, ICF system, used to build the teaching center within the garage building. ICF construction consists of polystyrene foam panels with strong plastic connectors and steel rebar to make foam blocks that are stacked, creating a form for pouring concrete walls. The result is steel-reinforced concrete walls with thick insulating foam. So construction is fast and with practically no material waste. In fact, a class of LSU construction management students built the ICF walls in 2 weekends with training and supervision from the experienced contractor. These ICF walls provide continuous R22 insulating value with uniform expanded polystyrene foam on both sides. The wall system is also inherently airtight. When combined with an air-sealed ceiling or unvented roof and airtight windows and doors, ICF can produce a highly energy-efficient building. Since ICF walls contain a 6-inch thickness of steel-reinforced concrete with steel rebar embedded in the slab, it is an exceptionally strong and wind-resistant wall system. In fact, ICF can be engineered to create a tornado-safe room that meets FEMA standards. Solid concrete walls are safe from termite damage. However, termites can tunnel through the foam, so the foam is 8 inches above grade to prevent hidden entry, and borate-treated structural wood was used for the roof rafters, decking, and window bucks, so the structural building cannot become food for wood-destroying insects. In part 2 of this video, you will see how the ICF LaHouse Teaching Center was assembled from start to finish and why. LaHouse Insulating Concrete Form Building System from the ground up. The slab foundation was built to protect the building. Long-lasting chemical soil treatment provides termite protection. A strong 6mm vapor barrier lines both the flat ground and the trenches all the way to the surface grade to prevent wicking of moisture from the ground. And a post-tension system was used to protect the slab from our expansive soil conditions. The slab is 8 inches above grade for easy termite tunnel inspection. During slab formation, rebar was embedded every 4 feet into the slab perimeter before it cured. This served to secure the walls to the foundation. Each pre-manufactured rigid foam wall panel has sturdy, high-density plastic webbing embedded in it. Connectors were snapped in place on site to create the 12-inch thick wall forms specified for LaHouse. The forms were placed along the slab perimeter and stacked layer by layer, with adhesive applied between the layers. Both horizontal and vertical rebar was installed inside the forms for each layer. The foam forms were easily cut to fit the door and window dimensions. The openings were lined with pressure-treated wood bucks for framing to attach the door and window units. After the foam forms were stacked to full height, temporary braces were installed on the interior and corner reinforcements on the exterior to support the forms during the concrete pumping. The bracing kept the walls straight and even and helped to prevent breakthrough. Then, a low-water to cement ratio of concrete was gradually pumped into the forms in layers to fully fill the cavities and to prevent blowouts from too much pressure. Before the concrete fully cured, treated wood top plates were installed with anchor bolts, same as is done in a slab foundation. Metal plates tied the top plates to the rim and the joists, and metal twist straps wrap over each roof rafter and tie it to the rim framing. Borate-treated roof rafters and decking panels offer high strength and moisture performance as well as decay and termite resistance. The fortified roof decking is 19/32 inch thick and attached with ring shank nails at 6-inch spacing to resist pullout from uplift. Notice the decking is also marked with a grid to make installation faster and more precise. For a hurricane-fortified roof, the roof decking seams were taped with a roof-tolerant tape to form a secondary water barrier. The synthetic roofing underlayment installed is extremely tear-resistant. In fact, before the roofing was installed, this underlayment survived both Hurricanes Katrina and Rita without one tear. All windows and doors are impact-resistant units with break-resistant insulated glass for protection from flying debris and providing high security. The garage door is insulated to R9 and reinforced for high wind design pressure and impact resistance. A typical garage door is normally the most vulnerable opening in a home during a hurricane, and its failure can lead to major structural damage. In addition, a waterproofing coating was applied to the bottom 3 feet of the exterior walls. This enables the building to be dry flood-proofed with watertight flood enclosures installed at the doorways. Dry flood-proofing can qualify for flood insurance in commercial buildings, but not in homes. To top off the building's energy-saving features, R38 stabilized cellulose insulation was installed over a sealed ceiling. A cool color metal roof is installed. The special heat-reflective paint gives the dark brown color the solar heat reflectance of a light color, qualifying for an Energy Star label. Of course, the metal roofing is also very durable, installed for high wind resistance, and is a standing seam, snap lock seam type of roofing. Since it has no exposed fasteners, it needs less maintenance and is less prone to leaks. A few points to consider. Plumbing and electrical channels are a simple process, but penetrations, alterations, and structural attachments involve drilling into concrete. Siding and other attachments need to align with the embedded webbing or go past the thick foam into the concrete. Using this technology to best advantage requires training, experience to get past the learning curve, and specialized equipment. ICF building systems typically cost 5 to 10% more than standard construction, but that investment provides extra high performance in durability and energy efficiency. It is especially well suited to coastal areas and may qualify for more favorable insurance terms and discounts. To pass along some lessons learned. All construction workers need detailed guidelines in how to properly attach things to ICF walls, since there is 2.5 inches of foam to penetrate before reaching concrete or the plastic connectors. With less on-the-fly flexibility, all dimensions, details, components, and methods should be fully determined and specified before beginning. Correcting errors requires a jackhammer. In summary, insulating concrete form construction is an innovative system that offers fast, labor-saving, low-waste, energy-efficient, and exceptionally strong wind and flood-hardy building for the higher investment and a higher performance. You're invited to explore LaHouse inside and out, its cutaways, feature signage, models, publications, library, and the website, and to learn about how you can shape your future with a high-performance home.